Consider the back of your hand for a moment. The skin, the bones beneath it, the blood moving through the veins you can trace with your finger. It feels entirely familiar, entirely local, entirely yours. But that intuition is one of the most profound illusions in all of science. Because the atoms that build every cell in your body, every molecule of hemoglobin carrying oxygen through your arteries right now, did not originate on this planet. They were not born in any process connected to Earth's geology or its oceans or its ancient chemistry. They were forged in the cores of massive stars that burned out billions of years before our sun ever ignited, in events of such catastrophic violence that the energy released in a single second exceeded what our own sun will produce across its entire 10 billion year lifetime. You are, in the most literal physical sense that science can offer, a collection of ash from dead alien suns. To understand why that is not a metaphor but a hard physical fact, we need to go back, not just to the beginning of Earth, not just to the beginning of our solar system, but to the very beginning of matter itself. In the first few minutes after the Big Bang, the universe was an extraordinarily hot, extraordinarily dense sea of particles and radiation. As it expanded and cooled, protons and neutrons began combining through a process we call Big Bang nucleosynthesis. The physics of those first minutes was governed by the interplay between the rate of expansion and the rate of nuclear reactions. The universe was cooling so rapidly that the window for nuclear fusion was extraordinarily brief, perhaps only a few minutes wide. What came out of that window was a universe composed almost entirely of hydrogen, roughly 75% by mass, and helium, roughly 25%, with trace amounts of lithium and essentially nothing else. Pause on that. A universe made almost entirely of two elements, hydrogen and helium. There is no carbon in that early universe, no oxygen, no nitrogen, no iron, no calcium, no phosphorus. None of the elements that biology requires to construct even the simplest living cell. The early universe was, from the perspective of chemistry, almost completely sterile. The periodic table as we know it, that rich catalog of over 90 naturally occurring elements, did not yet exist. It had to be built, and the factories that built it were stars. But to understand how stars build heavy elements, we need to understand something fundamental about the nucleus of an atom. Every atomic nucleus carries a positive electric charge because it contains protons, and protons are positively charged particles. Now, like charges, repel. This is one of the foundational rules of electromagnetism. So when you try to push two atomic nuclei toward each other, you are fighting against a repulsive electromagnetic force that grows stronger the closer those nuclei get. This electromagnetic barrier is called the Coulomb barrier, named after the French physicist Charles-Augustin de Coulomb, and it is one of the great obstacles in nuclear physics. Think of trying to roll two identical magnets together with their north poles facing. The closer they get, the stronger the repulsion. Now imagine that repulsive force is 1,000,000 times stronger, and the magnets are the size of a proton. To overcome the Coulomb barrier and force two nuclei close enough together for the strong nuclear force to grab them and fuse them, you need enormous kinetic energy. You need temperature. Temperature, at the atomic scale, is simply the average kinetic energy of particles. Higher temperature means particles are moving faster, colliding harder. And in the core of a star, the temperature is measured in millions of degrees. A star like our sun forms when a cloud of hydrogen gas, accumulated in some quiet corner of a galaxy over millions of years, reaches a density sufficient to trigger gravitational collapse. Gravity is relentless. It pulls inward from every direction, and as the cloud collapses, the material in the center is compressed with increasing ferocity. Compression generates heat. The core temperature climbs and climbs and climbs until it reaches approximately 10 million degrees Kelvin. At that temperature, hydrogen nuclei, which are simply protons, are moving fast enough that some fraction of them can tunnel quantum mechanically through the Coulomb barrier and get close enough for the strong force to fuse them. This is the proton-proton chain, the dominant fusion reaction in stars like our sun. Two protons collide and fuse, but the resulting nucleus is unstable. One proton converts into a neutron through the weak nuclear force, emitting a positron and a neutrino in the process. What remains is deuterium, a hydrogen nucleus containing one proton and one neutron. That deuterium then fuses with another proton to produce helium, 3, a nucleus with two protons and one neutron, releasing a gamma-ray photon. And finally, 2 helium, 3 nuclei collide and merge, spitting out 2 protons and leaving behind helium, 4, a nucleus with 2 protons and 2 neutrons. The net result of the entire proton-proton chain is that 4 hydrogen nuclei have been converted into 1 helium, 4 nucleus. And here is the key. The mass of 4 separate protons is slightly greater than the mass of 1 helium, 4 nucleus. That mass difference, tiny as it is converted directly into energy according to Einstein's relationship between mass and energy. This is the energy that makes a star shine. It is the pressure of this outward-flowing radiation that counteracts the inward pull of gravity and keeps a star from collapsing under its own weight. A star is, in this sense, a perfectly balanced gravitational compression machine. Gravity is always trying to pull the star inward. Radiation pressure is always pushing the star outward. As long as there is fuel to burn, the balance holds. But the fuel is finite, and when the fuel begins to run out, something remarkable and violent follows. For stars much more massive than our Sun, perhaps 8 times more massive or greater, the story after hydrogen fusion is just the beginning. When the hydrogen in the core is exhausted, the core contracts and heats further. At around 100 million degrees, helium fusion begins. The helium, 4 nuclei that the star spent its hydrogen-burning lifetime producing, now become the new fuel. But helium fusion presents a far more difficult problem than hydrogen fusion because helium nuclei carry twice the charge of protons, and the Coulomb barrier is therefore significantly higher. The first step in helium fusion requires a collision between 2 helium, 4 nuclei to produce beryllium, 8, but beryllium 8 is extraordinarily unstable. It decays back into 2 helium, 4 nuclei in an almost unimaginably short time, around 10 to the power of -16 seconds. This instability presented a deep puzzle in early nuclear astrophysics. How could carbon ever be built if the intermediate step, beryllium 8, vanished almost immediately after forming? The answer was one of the most elegant pieces of nuclear physics ever discovered. The astrophysicist Fred Hoyle predicted in the early 1950s that carbon-12 must have an excited nuclear energy state at a very specific energy level. If it did not, he argued, carbon could not be produced in stellar interiors in any abundance, and since we are made of carbon, and we exist, carbon must be produced, therefore the energy state must exist. He was right. The excited state of carbon, 1,2, now called the Hoyle state, allows a third helium, 4 nucleus to be captured by the unstable beryllium, 8 before it decays, completing the triple alpha process and producing a stable carbon 1,2 nucleus. This is not a lucky coincidence. It is an example of physics aligning in a way that allows carbon-based chemistry to exist. The triple alpha process is the bridge between the sterile early universe and the rich, complex chemistry that makes life possible. From carbon, a 4th helium nucleus can be added to produce oxygen 1,6. Helium burning therefore produces both carbon and oxygen, the 2 elements most central to organic chemistry, in considerable quantities. The star is now generating energy from a new fuel source, and the outward radiation pressure is once again sufficient to hold off gravity. But the core is only getting hotter and denser as these reactions proceed, and in a massive star, the story continues far beyond helium burning. When helium is exhausted, the core contracts again, temperatures rise further, and carbon fusion begins, producing neon and magnesium. Neon then burns to produce oxygen. Oxygen burns to produce silicon and sulfur. Silicon burns in a complex cascade of nuclear reactions to produce elements near the peak of the periodic table, including nickel and, most critically, iron. The architecture of a massive star in the final stages of its life is a series of concentric shells. The outermost layers are still hydrogen. Below that, helium fusion is occurring. Below that, carbon, then neon, then oxygen, then silicon, and at the very center, an iron core, growing steadily more massive with each moment. Iron is the end of the road for stellar fusion. This is a hard physical fact rooted in nuclear binding energy. The binding energy of a nucleus is the energy required to pull all of its protons and neutrons apart into separate particles. Iron, 5,6, has the highest binding energy per nucleon of any nucleus. This means that fusing two iron nuclei together does not release energy, it consumes energy. For every element lighter than iron, fusion releases energy. For every element heavier than iron, fusion costs energy. Iron is the point of no return. When the silicon-burning shell deposits more iron onto the iron core, the core gains mass but gains nothing in the way of energy generation. The outward radiation pressure from the iron core begins to fail. Gravity, patient and relentless, begins to win. The core contracts. As it does, its density rises until electrons are forced into the nuclei, where they combine with protons to produce neutrons and neutrinos in a process called electron capture. The core is neutronizing at a catastrophic rate. What happens next occurs in a fraction of a second. The iron core, now approximately the mass of our sun compressed into a sphere roughly the size of a city, collapses from a radius of several thousand kilometers to perhaps 10 to 15 kilometers. The outer layers of the star, no longer supported by the core, begin to freefall inward. When the infalling material hits the incompressible neutron-dense core, it bounces. The shock wave that propagates outward from that bounce, amplified by an enormous outpouring of neutrinos from the collapsing core, tears the star apart. The explosion we call a core collapse supernova releases more energy in 10 seconds than our sun will radiate in its entire 10 billion year life. And in that explosion, two extraordinary things happen. First, the shock wave and the intense flux of neutrons passing through the outer layers of the star drive nuclear reactions that produce elements heavier than iron, including cobalt, zinc, silver, gold, and iodine, elements that simply cannot be made by any fusion process inside a living star. Second, the stellar material, all of those oxygen and carbon and silicon and iron atoms that the star spent millions of years assembling, is hurled into space at a significant fraction of the speed of light. The star, which was a prison for the elements it created, is destroyed, and in being destroyed, it fulfills its most profound physical function. It distributes the products of billions of years of nuclear cooking to the surrounding interstellar medium. There is a second category of events that produces heavy elements in even greater abundance, and which was confirmed observationally only within the last decade. When two neutron stars, the dense remnants left behind after supernova explosions, are orbiting each other in a binary system, they spiral inward over millions of years, radiating energy as gravitational waves until they collide in a cataclysm called a kilonova. The densities and neutron fluxes reached in a kilonova are so extreme that the rapid neutron capture process, known as the R process, operates with extraordinary efficiency, building nuclei all the way up to uranium and beyond. In September 2017, the LIGO and Virgo gravitational wave detectors registered the merger of two neutron stars approximately 130 million light-years away, and the electromagnetic follow-up observations confirmed the production of gold and platinum and other heavy elements in quantities that had only previously been theorized. So the iron in your blood was seeded into the early solar system by supernovae that exploded before our sun formed. The gold in a ring, if you happen to be wearing one, most likely came from a neutron star merger that occurred billions of years before Earth existed. The calcium in your bones, the oxygen in every breath you take, the carbon that forms the backbone of every organic molecule in your body, every one of these atoms was assembled inside a stellar furnace or in the violent aftermath of a stellar death. The universe spent its first billion years arranging for these events to occur. Gravity organized the hydrogen and helium of the early universe into galactic structures. Those structures formed the first generation of massive stars, which lived fast and died violently, seeding the interstellar medium with the first heavy elements. Second and third generation stars formed from clouds enriched by those explosions, continuing the cycle, building still richer elemental abundances. Our sun is a later generation star. The cloud of gas and dust from which it formed, approximately 4.5 billion years ago, was already richly seeded with the products of earlier stellar generations. The rocky material that coalesced to form Earth was drawn from that enriched cloud. The calcium and iron and oxygen and carbon that existed in that cloud became rock, became ocean, became atmosphere, became the raw material for the first self-replicating molecules. And those molecules, through a long sequence of physical and chemical processes still under active scientific investigation, eventually gave rise to cells, to organisms, to the full complexity of biosphere that ultimately produced a brain capable of asking where all of this came from. When you look at the night sky and see the faint smear of light we call the Milky Way, you are looking at a galaxy full of stars, some of which are in the process of building the atoms that will one day be incorporated into bodies like yours, on planets like this one. The cycle of stellar birth and death is ongoing, and you are one of its products. The atoms in your body are approximately 14 billion years old, almost as old as the universe itself. They have been inside other stars, inside interstellar clouds, inside the early Earth. They will be inside other bodies after you and other planets and perhaps other stars long after the particular arrangement we call a human being has dissolved. Matter persists. Arrangements change. And the process by which simple hydrogen nuclei produced in the first minutes of the universe become the organized complexity of a living mind capable of contemplating its own atomic origins is perhaps the most extraordinary physical story that science has ever uncovered.